Hey, year 13s, thanks for coming, guys. So I'm going to crack straight on today. So look at this, infinite Tobies. Ooh, look at me wave, look at that, infinite Tobies. I'm doing my own Mexican wave. Amazing. Right, let's crack on. Share screen. I should bring in my little clip cam, shouldn't I? Right. Year 13, there we go. So we've already, we've finished carbonyls. Last time we looked at testing. We then looked at a homework and we were doing some reactions of them. More practice, obviously, is there on tests if you want to do it. So today's lesson, we're going on to carboxylic acids. So let's crack on. So this is A2. Now, by the way, technically, if you're interested, this is Unit 4 for EdXL. Unit 4, and this is carboxylic acids. 3 learning objectives. Number 1, know the properties. Actually, you know what? I should probably have some kind of continuity here. So if I just go edit, I can just select. Oh, that's not going to let me do that. I need my mouse. 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 I've got a mouse. Ignore me. I'm sorry.
Properties.
I haven't got a mouse. I forgot my mouse. No! I can't find my mouse.
Don't they have those like
I had. No, I've forgotten my mouse. I think I've forgotten my mouse. It doesn't matter. No mouse. Okay, draw, name, properties making. Draw, be able to draw, continuity. Be able to draw and name. Draw and name. So straight away, question number 1. Yeah, we know the games. Yeah, we know the games. Name it, guys. Question 2.
1, 2, 3, 5.
There we go.
Wait. Oh, that's number 2. Oh, that's the different one. 1, 2, 3, 4. Ethanol.
Okay. Oh, switch to a different color. Wink it.
Oh, that's 2. Oh, technically, you need to say the 2.
Technically, no, but I prefer you if you did.
2,2-dimethylpropanoic.
Thank you very much. 2,2-dimethylpropanoic acid, nice and easy. It's nice to see a skeletal then, isn't it? Methylpropanoic. Julian? Yeah, one just skeletal. Yeah, butanoic acid, nice and easy. Butanoic acid. They're not going to be that easy, of course, at A2. They're going to give you something like this. They'll probably give you that's much more likely. And then we can do that one's much more fun too. I'd quite like to see an oic skeletal. So we actually see a real skeletal. By the way, guys, name that one. That one's much more A2 level. I wonder how many people will get it right. Oic skeletal. Carboxylic acid. Let's do propanoic.
That's a 4, right?
Yeah, exactly as I've done it, which is fine. This one, of course, guys, is a classic. I'm just reminding you at A2, do not forget your EZ.
Oh.
Easiest thing in the world to miss. If you see an ene, just don't forget to check for geometrical. Yeah, this does show geo, and they've shown it. So this is going to be 1, 2, 3. So that's but, and it's and we're going to number it from this direction because you always go from the carboxylic acid. So this is a 2E. The E vanishes, of course, becoming an oic acid. Oh, no dash needed. You don't put dashes. Enoic acid. But then, of course, we've got to remember that this is an E because the H's are on opposite sides. Yeah, really, just don't forget that's how they make this A2. Yeah, clever games all. Okay, so we know we need to practice this. We're going to be practicing this, guys. You know where I'm going to send you. You need to go to Doc Brown. Yeah, I need you guys to be doing Doc Brown every day on naming. I don't care which quiz you do, which one you pick, just be doing 20 questions a day. Dixon, that's me focusing on you, please. You need more practice at this, Dixon. Please, please do it. Right, properties. 2 properties that they're now going to ask you to know about carboxylic acids. Boiling point and solubility. So this is not actually particularly complicated, and it just requires a couple of bullet points. So first of all, we're going to do boiling point. So boiling point of oics. Bullet point number 1. They are higher than expected. Higher than expected. The reason why we know, the reason why is they dimerize. Yeah, we've already covered this in previous lessons. I'll now draw it for you. Yeah, so what's going to happen is the ethanoic acid will dimerize with another ethanoic acid. I should have gone for methanoic, kept it shorter for myself. Yeah, these are going to dimerize. Yeah, they're going to dimerize, and they dimerize in this rather cool fashion. Here's the hydrogen bonds. You've got to show the lone pair. Yeah, there's the hydrogen bond. You've got to show your deltas. All deltas must be shown. All lone pairs on the atoms involved must be shown as well. There we go. So they form a dimer via 2 hydrogen bonds. Go on, okay? You don't need it. It's not important. They won't care. Yeah, good question. I'm glad you asked. Winkit just asked me, do I need to include this one here? And the answer is no. They don't care about that in terms of the hydrogen bonding. It's because it's not involved, Winkit. Yeah, but you need it on all the other atoms, including all the various... I mean, to be fair, if I was in an exam, I'd want to give that its lone pairs as well, just because I can. Do you know what I mean? Yeah. Just always whack 2 lone pairs on oxygen. So because they dimerize, their MR is effectively ×2, which leads to a higher boiling point than expected. Not particularly complicated, but we just need to know that they do it. So the MR doubles, so higher than expected, higher BPT than predicted. So not only, in order to melt these, you can see what's going to be done. Not only are you going to have to break the larger van der Waals between the dimers, so the van der Waals are higher, plus you'd have to separate these dimers into 2 separate, which means 2 hydrogen bonds per pair. And that's much more force than is usually seen. They expected these, don't get me wrong, you expected to see 1 hydrogen bond per molecule, because the limitation is the hydrogen on the O. So so by the way, we can actually prove this. So the MR of ethanoic acid, let's actually make it easy for ourselves. Yeah, ethanoic acid, yeah, I think it has an MR of 60, I believe. That's what number's in my head. Can someone run that for me? So hang on, calculator, 12 plus 3 plus 12 plus 16 plus 16 plus 1, 60. Has an MR of 60. So what we could then argue is, well, let's construct something that has an MR of 60, which is similar. So what about, and it needs to also show hydrogen bonding. Would you agree with this? Yeah, this makes sense, because so we could build something. Let's go for propanol. What's the MR of propanol, please? Someone run that. It's going to be close. It's got to be close to 60, that. Is it? Is it that high? 12 times 3 plus 16 plus 8. 60! It's the same. It has the same MR. So what that means is we should be able to see exactly the same boiling point between these two. They both form one hydrogen bond per molecule, and they both have the same MR, so the London dispersion forces or any other exam boards van der Waals forces will be identical. So these melting points should be exactly the same. So we now need ethanoic acid boiling, go 118 degrees Celsius. So that's 118 degrees C. What's propanol? Let's now do, fingers crossed. If this is all wrong, by the way, then you can ignore everything I'm teaching you. 97, there you go, it's higher than expected. 97, so it's 20 degrees higher than it should be. And that's a relatively, I know that people go, it's not how much, is it? I mean, like, come on, it's only 20 degrees. But actually, you know, 20 degrees at this particular level makes a big difference. By the way, it's nice to also at this point to mention ethanoic acid, since I brought this up. So ethanoic acid, we know that there are two versions of it. We have got aqueous, that is ethanoic acid. Ethanoic acid. And how do I know it's aqueous? Because it has the word acid after it. There's another one. There's pure ethanoic acid, which is called glacial ethanoic acid. I know glacial. Yes, like ice. I can't spell it. Is that it's called glacial? Is it an A? I knew I was going to get it right the first time. Darn it. Glacial. By the way, sometimes called acetic acid. They shouldn't really add the acid in because it's pure. But the glacial bit tells you it's pure. Now, just to tell you why, it's because it has a higher melting point than expected at over 120. What happens is, if you have a bottle of this stuff, it forms what look like icebergs. Yeah, they are big lumps of acetic acid floating around in it. This is when no one's going to have a picture. Because it literally looks like they've got like little icebergs like floating around. Yeah. There you go. I like what you've done there, Julian. I like it a lot. Global warming stopped acetic acid forming its glacial types. You can't photograph it anymore. Love that. Yeah, so you tend to get, there's no really good pictures of it. Because back in my day, we had huge bottles of this stuff in my school. And when you pulled out this massive bottle, you could just see these lumps that look like little icebergs just clattering around inside it. And what you knew, it was really close then to its freezing point. So it's quite nice. It's just nice to mention that this here is pure. Yeah, this is, by the way, you could also call it, is everyone okay with me saying it's conc? Yeah, concentrate. We know that the word conc when it comes to acids means no water. Yes, okay. So boiling point higher than expected. The next thing, solubility. Yeah?
So for glacial, is it only acid or can you put it for any acid?
Good question. No, it's just for ethanoic. I don't. You're going to say why?
Yes.
Do you know what? I say that. I don't think glacial propanoic acid. It's not going to be. The problem is someone may have written it. Glacial acetic. Yeah. Then if water-free anhydrous, you wouldn't do it. I know. Go figure. It's kind of like a common name, but the thing is though, it comes up on exams. Every now and again, it'll say, Stephen now adds 2 centimeters cubed of glacial acetic acid. And everyone goes, glacial? What you just need to know is it's pure, it's concentrated, there's no water. Yeah. Now we go to solubility. Now this one again, I can ask Wingkit being in the classroom. Wingkit, ethanoic acid. We know this guy, don't we? Can you give me its common name from the shops, please? Thank you very much. So here's my question then. If this is vinegar, is it soluble? Really? Do you have lumps in your vinegar?
No, we don't.
So it definitely is soluble. So we know that it is. The answer, of course, is yes, because we know there is our vinegar is not cloudy.
Yeah.
So then the next question to you, Winkit, is why is it soluble? Thank you very much. We know this question. Add it into our notes. Ethanoic acid, CH3, let's keep it easy for myself, can form hydrogen bonds to water. Can form hydrogen bonds to water molecules. This kind of makes sense. And by the way, and they do this regularly, they will say in the exam, draw the formation of hydrogen bonds between one molecule of ethanoic acid and one molecule of water. We know this. We've seen this a lot of times, haven't we? Yeah, we've seen these questions over and over. Yeah, we know that they like us to be able to draw hydrogen bonds. Why do they like it? Because, of course, they know that students do it badly. Yeah, so now, once you get to this point, all your deltas of the people who are important must go on. All of them. Then you must show all your lone pairs. Yeah, there and there. And then this one's important because you must have your hydrogen bond lines leaving from a lone pair. The most common mistake is that people draw this image, yeah, and they put their lone pairs here, and then their hydrogen, that's wrong. Yeah, we know in reality it is living inside the orbital of those lone pairs, hence why it's so important. Yeah, so they must leave from that lone pair. There's your hydrogen bond, and we're done. That's a HB. Gotta love a good HB. Not complicated. By the way, you also realize that there are other options. We could have also done this if you liked. How about this guy? How about this one? We could have done this. Going to a H. Ooh, can do that. Happy with that guy. Lone pairs on. There we go. Totally okay with that. Yeah. So we realize that they are soluble because they can form these hydrogen bonds. Yeah. Well, hang on a sec. What would happen if the chain got longer? Thank you. So here's our one nota bene. As chain length increases, solubility decreases. That's all you need to know. Solubility decreases. The reason being is that if you were going to look at this like an image, so I'm just going to go water, 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 water. This is just pure, guys, this is pure. Okay, I'm not going to like that. If I do that, I'm going to hate myself for it. Let's do a whole load of water molecules. Yeah. So here's our water molecules, our V-shaped water molecules. Let's then show our hydrogen. I'm going to do another one as well. There we go. Let's then show our hydrogen bonds. Here they are. Hydrogen bond, hydrogen bond, hydrogen bond. Oh, got to be careful where that's going. Yeah. And then hydrogen bond here, hydrogen bond there, hydrogen bond there, hydrogen bond here, and here. 2 per molecule. Agreed? Yeah, there we go. Right. So if you were then going to add an oic into this, the reason why it dissolves is because this H here can now form these hydrogen bonds. Agreed? So can this double bonded O. It can be done. So it will slot in and push the waters aside. But the longer the chain, as the chain gets longer and longer, you have to push more and more waters aside as it enters into the system. Does that make sense? Yeah. So eventually, because the chain can only form London dispersion forces, means that eventually they'll just become insoluble entirely. Yeah. And by the way, it's surprisingly short. So we can actually look up some values, which I think would be of interest. Winkit, have you got your laptop there? Yep. Can you do me a favor? Can you look up the solubility for ethanoic, please? So let's go first. Solubility. Later on in the show. Solubility, it'll give us it in grams per 100 grams, probably.
It says here, so it's
Grams per liter?
bigger than or equal 100 milligrams per milliliter, which is
Ooh, 100. Hang on a minute.
grams per liter.
That's grams per liter. So that's 100 grams per liter.
Bigger than or equal to?
That's okay. So hang on, what was your number?
100.
100 grams per liter.
Let me just double check.
Yeah, what you actually gave me 1 milligram.
Milligram per milliliter. Sorry.
1 milligram per milliliter. What the hell? That's weird.
Milligrams per milliliter.
Oh, 100 milligrams per milliliter. So, by the way, I hate milliliters. It's biology squishiness. That's a centimeter cubed, right? So that also then translates to 0.1 of a gram, 0.1 grams per centimeter cubed. It's the same thing as 100 milligrams. Agreed? Yeah. So what that means is if I multiply this up by 100, yeah, then I multiply this up by 100, so it's 10. Oh, centimeter. Yes, there is. Sorry. Centimeters to liters is 1,000. Sorry. Winkit is absolutely correct. Yeah. Yeah. So you're absolutely right. 100 grams. So prediction. Julian, because Winkit's on the laptop. Julian, methanoic acid. Higher or lower, please? Well done. Winkit, can you now do methanoic, please?
I just go on 150.
Oh God, you know what? Now that's much more of a fun game. Could you actually predict the increase? It's going. Do you know what? It's gonna be a massive increase because all of a sudden you don't have to break those hydrogen bonds. The molecule's much smaller. It's gonna be like 4 times higher, isn't it?
It's called formic acid.
Formic acid, isn't that what?
And it's like
Yes, correct. It does depend on the ounce, for sure. Red ants, I think, can inject formic acid.
Find the solubility. It's great.
Go on.
Greater than or equal to 100.
Is it the same number? No.
This is greater.
I know. I realize that.
Okay, wait, I can check the ethanoic one because they have this different like values. For let me just go back.
Solubility in water, it just says miscible. Oh, you suck.
Just give me a sec, sir. It says okay. It says for acetic acid or ethanoic acid, it's 16.65 N.
Okay. Oh, that's interesting. 16. Yeah, molarity. Sure.
But then for methanoic,
Yeah.
it says 21.73.
Now that makes more sense. The max concentration. That makes sense. So it's an extra 25%, give or take. That's cool. I like it. Right. So what about then? Let's make this really long. Let's go for hexanoic acid, please. Is it miscible? Hexanoic.
Sorry, give me a second.
I just want to know how long it takes before it stops being soluble. Hexanoic acid.
5 more.
By the way, if I was going to guess, I would say that's no longer
It's
soluble.
0.09 M. It's 5 to 10 milligrams per milliliter.
So it's basically, it's 5 milligrams per liter. Wow. 5 milligrams per liter. Lol. That's so small. Whereas this one had 16 molar. We could even work out the actual value there, but we're not going to bother. The answer is it's no longer soluble. So you realize that it only requires a small increase to stop it being soluble entirely. Right. Next thing. So we've done boiling point. We've done solubility. We can tick off the properties. What I now want to do is I want to do making and reactions. How are we doing for time? We've got another 10 minutes. Let's do making. Let's just do making today since it's on my learning objective. Then tomorrow we can do the reactions of. That's a good idea, right? I like that. That's good. Making of oics. So, guys, how do you make them? So, number 1.
PCO5.
Ooh. Ooh.
No.
Please don't. Yeah, that's definitely not right. The brilliant. Oh my goodness. Well done. Right. So Winkit's thrown me a primary ol. So we could take a primary alcohol. Oh, thank you, Julian's given. We now oxidize, but it must be under reflux, and we also should have an excess of the oxidizing agent. Is that okay with that, guys? Makes sense? Yeah. We know that we can take an ol, we can oxido an aldehyde and then onto an oic. So if we wanted to skip it, if we wanted to make the oic, we would do reflux, oxidizing agent, yeah, excess, and it will go all the way. Number 2, we can do this with a secondary alcohol, can't we? Yeah, number 2, a secondary alcohol. Secondary alcohol. Right, once again, this is an oxidizing agent, such as potassium dichromate. Yeah, we'll still do it in excess. And here's the hilarious bit. We're still going to do it under reflux. And the question is why? This is the clever bit. What we realize, oh, hang on. No, this is garbage. It won't do it, will it? So in fact, you can't get it from that. So take it back. It doesn't work because you're going to end up with a ketone and it won't form the OIC. So how else could you get to an OIC? The next one is the hydrolysis of nitriles.
Ooh.
So we can take this family, R bond C triple bond N. I'll put this underneath as RCN. We can even do a real one if you like. Yeah, but we can now hydrolyze this. Now, I'm wondering how many of you guys are going to be able to guess. So in terms of a mechanism-wise, in terms of a nitrile, what would you expect it to do? Would you expect it to react with, Julian, nucleophiles or electrophiles? So what's the can you give me an electrophile, please? Weight's about right. Name me an electrophile. Give me a benzene electrophile. Thank you. Cyanide minus. Give me another benzene electrophile. H minus. Come on, Julian, you're better than this. Yeah. Electrophiles are electron pair donors. Is a negative thing going to go anywhere near that triple bond? No, we know that this is a region of high electron density. We need to attack this with a nucleophile. Yeah, we're going to attack this with sodium hydroxide, a strong nucleophile. So we're going to now react this with sodium hydroxide, NaOH, and water. It's the OH minus that's doing it, yes. In terms of, it's going to be fun to try and build this mechanism in a minute. And what you will end up with, now here's the important bit, guys. Because remember, what we're trying to make here is a carboxylic acid. What condition are we currently in?
Alkali.
We're in alkali. What that means is we're not going to form the OIC, are we?
No.
We're going to form the salt. We're going to form, in this reaction, we're going to form the carboxylate salt. We're going to get COONA. And what else are we going to get? We're going to end up with probably, oh, well, the nitrogen has to go somewhere. Is that going to go off as ammonia? It could do.
Yeah,
Oh.
it looks like it balances, sir. Because we have
Does it
O's.
really?
We have two O's. No, because we have two O's, and those are used up in the COO. We have one
3 H's?
and 3 H's.
No way, that can't happen. No way does that happen. Hydrolysis. Hydrolysis of nitriles. Images. What's the byproduct? No one ever talks about the byproduct.
Who cares? We have enough ammonia as it is, you know.
It forms, it looks like it forms ammonia. Oh my God, byproduct. It actually does it. And there's the mechanism.
Oh, guys, copy this quickly. Go.
That's really cool. Tautomerism. It's got tautomerism in it. Look at that. That's so cool. Oh, it actually forms ammonia. That's hilarious. It does actually. That's brilliant. So, I was going to have a go at building that then. By the way, so guys, we're not finished though. So the hydrolysis of nitriles, stage 1. Step 1 is to reflux with sodium hydroxide solution. And you'd probably do it conc too as well. Well, you wouldn't really use conc sodium hydroxide. You'd use a high concentration. They wouldn't really care. Reflux with sodium, but there is now a second step. If you want the oic, what do I now need to do to that? I'm now going to turn it back into the oic. Winkit, how do I turn the salt back into the oic? Add H+. We're going to add an acid. Yep, that's correct. Add H+. We're probably going to add dilute sulfuric, probably. Dilute H2SO4. And what will then happen is you will turn it all the way. So it's actually a 2-step process. And then you're going to form sodium sulfate, by the way, at the outcome. So step number 2 is to add, add dilute acid. It'd be interesting to know what acid they choose. Do they... Say again? Oh, so it's a separate equation. It's a separate equation, Winkit. I can do that for you if you like. Okay, so the equation will be RCOO. I'm actually going to show the ion charges just for fun. Plus H2SO4 goes to form. And because sulfuric is a much stronger acid, my laptop has stopped doing anything. So this now becomes RCOOH and sodium hydrogen sulfate. That's it. Yeah, and if you want the charges on that as well, you can do for constant, just so you know where the charges are. Yeah, you're forming that technically.
Would you not form a Na2SO4?
The answer is yeah, you could do. You might. They wouldn't care what equation. If you want, but if you don't like the charges, I can get rid of those if you like. They're not really all that necessary. You could have a second reaction, Winkit, where you would have another one, another ROONA would also react with HSO4 minus. But the thing is, it's much less likely because in reality, the Na isn't there, is it? It's actually that. Yeah. Then now they're going to repel each other. But no, hang on a minute, but that's not entirely true because this dissociates. No, ignore me, Winkit. I'm talking garbage. Yeah. Because in reality, yeah, I know what you're saying. Yeah, you could do either. It's going to do both. Yeah, you could do either if you wanted. You can, in fact, what we can do is you can do this. Just double that and then form that. That works then, doesn't it? Yeah. So you can do that one as well. Either one. So it's a 2-step process. Add dilute, I missed it. Add dilute acid. Yeah, there we go. At the end of it, and it will turn it back then into the carboxylic acid. And then, of course, the melting point will increase and you can distill it quite easily. Yeah. Does that make sense? At this point, you distill off your carboxylic acid based on the fact that it's now going to have, you can, yeah, anyway. And that's all you actually need for the formation of carboxylic acids. You don't actually need any others. You cut, by the way, I will mention just one thing though, which is every now and again they do talk about the oxidation with air. So you guys know that if you leave wine out, yeah, it'll turn into vinegar. So one of the things that they do is when they make wine in the vineyards, the wine that isn't very good, they just put it into what's called an aerator, which is literally a wooden barrel which rotates. And as it rotates, it adds in air and oxidizes it up to carbon, and then they sell it as red wine or white wine. So you can have a set, you can do this with air, and every now and again the question, and what that happens is you just put in O2 in the equation and balance for it. Okay. Instead of using the brackets O, you actually use O2. That's the only difference. But otherwise, that's it. Carboxylic acids. Tomorrow we'll do reactions of. Cool. Yeah, so the one that they always tend to do is because they do it with ethanol. Yeah, so we know we're going to take ethanol. They talk about the vineyards use they oxidize the ethanol with air, and it just says write the equation, and of course all you're doing is this, remembering to balance with water as your byproduct, and then make sure all your, and I think, so you've got 6 hydrogens, all the hydrogens add up to 2 carbons, do the oxygens 3, that actually adds up. Yeah, that actually, it's all balanced at that point, amazingly.
Cool.
Yeah.
Oh, terrific.
Right, guys, I will end the lesson there. I love the fact that, there we go. Guys, I hope you found it useful. I'll see you tomorrow for the reactions of oics. See you later, guys.